Hello students, so let's try to solve one problem from DJ Griffith. That is, the book name is Introduction to Quantum Mechanics and the problem is 1.7 number. And we have to prove that time derivative of expectation value of P is equal to minus expectation value of space derivative of potential. So P is momentum and V is potential. So we can prove this problem into different way, but I am going to prove this with the help of Ehrenfest theorem, which is very short, which is very efficient method to prove this thing. So what is first Ehrenfest theorem? So in the Ehrenfest theorem, it is given, suppose I have any dynamical variable A, and we just want to see the time derivative of this A, or this is average value of particular A with the time derivative dt is equal to 1 upon I h cat, and we have commutation between A and H, and we have to take the expectation value of this particular commutation A and H plus expectation value of del A upon del T. 1 by I h cat is this part. We can prove this thing with the help of Schrodinger wave equation, but we can use this as a one particular theorem, which is popularly known as a what? Ehrenfest theorem. So now we can use this particular thing. Suppose I have Hamiltonian, and let's say this Hamiltonian is nothing but px square upon 2m plus vx, because we are just talking about one-dimensional system. And here this p is actually px. So we have to keep in mind this is nothing but px. And what we have to do, we have to just calculate d upon dt. Expectation value of px is equal to 1 upon I h cat, and we have to find expectation value of px and h, and we have to take the average value of this. And obviously this px is not explicit function of time, so this can be is equal to 0. We have this particular condition, so it is not explicit function of time, so we can put dpx del px upon del t is equal to 0. So the ultimate idea is that if we are able to calculate the commutation of px and h, then we can easily find the value of this particular the change the derivative with the time for the average value of px. So obviously we have to calculate between commutation between px and h. And what is this h? H is nothing but we have px square upon 2m plus vx. And we have to keep in mind that these all are operators. So this px will 100% commute with px square upon 2m, because this is kinetic energy. Momentum and kinetic energy is always going to commute. So our main agenda is that we have to calculate what will be commutation between px and v as a function of x. So what we will do, we will write this px in a position representation, that is minus I h cat del upon del x. So, and we have to find what is this value, this particular value. So this value is minus I h cat del upon del x, and this value is vx. So what we have to do, we have to put value some psi x. This can be some function of psi x. So obviously we know the commutation between A and B is nothing. A into B, suppose we have some commutation between A and B, that will be AB minus BA. And if we have psi here, we have to operate psi like this. So let's try to go for this particular commutation. So when we are going to calculate this particular commutation, let's go for step by step. So let me start from here actually. So we have px, vx and psi here, minus vx, px, psi. Now, if vx will operate on psi, that will be Vxi, and we have to operate Px on whole this thing. So this value is minus IH cat del upon del x Vx psi x. So this is very interesting thing. Here Px will operate on this. So we have Vx minus IH cat del psi upon del x, and this is the value. Now in the next part, what we are going to do, we have to just differentiate it first Vx, then for psi x. This is function of x. So we have minus IH cat del Vx upon del x psi x minus IH cat, and then we have keep my Vx as a constant, and then we have del psi upon del x. Now we will go for this term. This minus minus, this term is plus. So what we are going to do, we will just write this particular thing as plus IH cat, and we have Vx del psi upon del x. So we can see that this term and this term have same value, but the negative sign, though this term is equivalent, and we can cancel. So what we have actually the commutation of Px and Vx as a function of psi x is equal to minus IH cat del V upon del x psi x. So what will happen if we are going to equate the psi x on both sides? Then we have commutation of Px Vx is equal to nothing but minus IH cat del V upon del x. Now we will again put the value in the mainly Ehrenfest theorem, and we can get the final answer. So let's put it here, and I am just using this space to final conclusion. So what we have actually, this is nothing but Px, and we have to take the time derivative of this, and this value is equal to nothing Px and Vx, and we have 1 upon IH cat. And now this value is equivalent to minus IH cat del V upon del x. So this value is equal to 1 upon I, and we have to take the average value of this. So this will be minus IH cat, we can take outside, and we can take average value of del V upon del x. And this IH cat is cancel out, and we have finally d upon dt. So this will be expectation value of Px with respect, and we are differentiating expectation value of Px with respect to time is nothing but the expectation value of minus del V upon del x. So this is all about the thing we have to prove here. And this is actually the semi-classical theory, where if we have quantum mechanical measurement and if we are taking the average value of momentum, and we are just going for the time derivative, rate of change of momentum will be nothing but the external force on an average. So this is just a classical result from the quantum mechanical calculation. First we will do the quantum mechanical calculation, take the average, and if we are going to satisfy this thing, this is exactly whatever Newton's second law is going to say. So this is a wonderful problem. You can solve this problem into another method also, but this is very efficient method to calculate the thing. And this is coming from the basic formulation of Poisson bracket and time evolution of any dynamical system in the classical mechanics. And then from there, we will use the Schrodinger wave equation and finally land up to this point. And we can use the Ehrenfest theorem very efficiently in this type of problem. Thank you.